All right, let's get started. So, welcome to the 7th lecture of the Deep Reinforcement Learning series. Today's lecture is on natural policy gradient methods. So, before we get started with this week's content, we'll just briefly recap what we covered last week. So, last week was on PPO. We started by just discussing a little bit the architectures for policy gradient methods. So, how do you make your neural network? How do you set it up so that you can train it with a policy gradient method? We then talked about the relative policy performance identity, which we'll briefly recap at the start of today's lecture. We talked about the surrogate advantage, which is a way that you can measure the improvement of one policy over another using only data driven from the policy that you're trying to improve over. We talked about how you can optimize the surrogate advantage, and in particular, we talked about how PPO adjusts the surrogate advantage in its optimization. So the PPO clip objective, which tries to prevent the new policy from going too far away from the old policy. All right. So this week we're going to start by covering the core idea of the natural policy gradient as one algorithm and the Trust Region Policy Optimisation. So this is the pair of algorithms that we're going to cover today: NPG, natural policy gradient, and Trust Region Policy Optimisation, or TRPO. We're going to start with NPG, natural policy gradient, and we're going to phrase the problem that NPG is solving as an optimization problem. Then we're going to solve that optimization problem, or approximately solve it. And then we're going to discuss how you compute the update that you need to perform for natural policy gradient. And we're going to discuss two different ways of computing this update direction. So there's a naive method, and there's another method called the conjugate gradient method, which is much better in various ways. And we're going to cover both of these. Then we're going to cover TRPO and look at its optimization problem and various tricks that it applies on top of NPG that make it a superior algorithm. All right, so let's briefly recap policy gradient theory. So this is all stuff from our lecture on A2C, advantage actor critic. We're just going to recap it now. So A2C attempts to optimize the policy objective, and this policy objective, which has come up both in the A2C algorithm and in the PPO algorithm, is just this: calligraphic J, which is the expectation over trajectories sampled according to your policy of just the return, so the sum of all rewards across that trajectory. And this is the thing that you ultimately care about, right? This is the important thing that you're trying to attain or trying to maximize. And the way A2C works is by performing gradient ascent on this objective, right? So A2C just tries to optimize this objective by performing gradient ascent on it, right? So it does this by computing this gradient, and this is called the policy gradient. And we saw in A2C that it's given by this form, where the policy gradient is expectation over trajectories drawn from the policy of the grad log probability of taking each action weighted by the advantage that action has. And we discussed in the A2C lecture that the effect that this has is of these advantages act as weights, where you sort of fit preferentially to actions that are better than average, so has a positive advantage, and unfit from actions that are worse than average or have a negative advantage. So that's the function of these advantages here. They act as weights. And the advantage, just to remind you, is the value of the action minus the value of the state. This is the advantage function. Any questions about this? Cool. Okay. So we have recapped A2C. Let's just also recap PPO, because we're going to use a lot of the same ideas again. So PPO is going to make use of the surrogate advantage. So the surrogate advantage is I average across, is a function of both a new set of parameters that I'm trying to optimize and an old set of parameters. And I'm averaging across data drawn according to my old policy of the ratio of the probabilities times by the advantage. Right? So this thing is called the surrogate advantage. And we saw an argument last week for the fact that when these two policies are close to one another, so when these two policies are in some sense near to one another, the surrogate advantage is an approximation of the policy improvement. And by policy improvement, I just mean the value of the new policy, so the average return under the new policy, minus the average return under the old policy, so the difference in return, so the improvement of this new policy over the old policy. Any questions about this? Awesome. Okay, so let's move on to the core idea of the natural policy gradient method and the Trust Region Policy Optimisation. So the core idea is that we're going to try to maximize the surrogate advantage while minimizing a distance of the new policy from the old policy. So we know that the surrogate advantage approximates the policy improvement when the policies are close, right? And so the core idea is, well, let's try to maximize the surrogate advantage while sort of constraining the new policy to be close to the old policy. So we're going to have a measure of distance, and this distance is going to measure how far away is our new policy from our old policy. And we're going to try to optimize the surrogate advantage subject to a sort of constraint or penalty on how far away the policies are from one another. And the idea is that this will force our policies to remain close, and therefore optimizing the surrogate advantage when the policies are close is going to amount to optimizing the policy improvement, because when they're close, these two things are approximately equal to one another. All right? So this is the core idea that both of these two algorithms are going to build off. So as our distance metric, as our way of measuring how far away our new policy is from our old policy, we're going to use the average KL divergence, which I'll go into as the next step. Right. So this is going to be the KL divergence at a particular state. So I'm briefly just going to recap what the KL divergence is, what it measures, how to interpret it, let's start by looking at the KL divergence at a particular state S. So there's no bar over this D, it's just the KL divergence at a state S. And this is the expression that we have for the KL divergence, i.e. sum over actions. In the case of a continuous action space, this would be an integral over actions, but for simplicity, we're just considering a finite action space, so a finite collection of actions which we're going to sum over, the probability of the action under the old policy, and then the log ratio of the probability of the action under the old policy to the probability of the action under the new policy. Right? This is another way of writing this out, so we can just expand this log ratio as log probability old minus log probability new. The reason I've written it in this form is that this is maybe slightly more interpretable. So the way to interpret this, well, log probabilities correspond to how well does a particular thing explain data. So one way that we can interpret what we've got here is we're generating actions according to the old policy. And this first term is asking how well does the old policy explain that action selection. So the log probability of the actions under the old policy. So this is how well does the old policy explain this action selection. And this is how well does the new policy explain this action selection. This is the way we can interpret this. And then by some mathematical arguments, you can show that this is always non-negative, so it's always greater than or equal to 0, and is in fact only 0 when these two are equal to one another. So this is the sense in which it measures distance. The further theta nu or pi nu is from pi old, the higher this quantity, this KL divergence will be. Does anyone have any questions about this? I think probably most of you have seen the KL divergence before. I just want to go over it, make sure we're all on the same footing. Right, so the average KL divergence, I'm just going to take this measure that is a measure of the difference of the policies at each state, and I'm going to average it. So this is the KL divergence at a state S, which is what we saw on the previous slide. And then I'm going to average this across states drawn according to my old policy. And this is the average KL divergence, which I'm going to write like this, with a D bar, right? And for the sake of brevity, so this is just, I'm taking this KL divergence measure, which is a measure that at each state of the discrepancy between these policies, and I'm averaging according to states drawn according to the old policy. And for brevity, to make things shorter, throughout I'm just going to write it as this, D bar theta old theta nu. So this is the distance under the average KL divergence metric of theta nu from theta old. All right? Any questions? Cool. So this is our measure of distance between policies. Now we're going to turn to the natural policy gradient optimization problem. So remember that the structuring optimization problem for all of today's lecture, the thing to have in mind is we're going to try to maximize the surrogate advantage, which again approximates the policy improvement when these policies are close, while minimizing the average KL divergence. Right? This is the overall theoretical framework for today's lecture. All right? So how does NPG turn this into an optimization problem? Well, the way NPG turns this into an optimization problem is by saying, well, let's maximize a trade-off between these things. So I have alpha, which is going to be a weighting parameter that controls the strength of this trade-off, surrogate advantage minus average KL divergence. So to maximize this, I need to increase the surrogate advantage as much as possible while decreasing the average KL divergence, or not letting the average KL divergence get too high. So if I let the average KL divergence get very high, this term will dominate and I won't do a good job of maximizing this objective. If I don't increase the surrogate advantage, then I won't maximize this objective. So I have to increase the surrogate advantage while simultaneously remaining close in this average KL divergence distance. And this alpha here is a weighting that trades off between increasing surrogate advantage and keeping d bar, keeping the average KL divergence low. All right? Any questions? Also, yeah?
Why is the alpha on the advantage rather than on the divergence?
Yeah, so provided alpha is positive, it's equivalent to have them in either place, right? For the sake of what result you end up getting out of this optimization problem, it's notationally nicer to have it here. So that's why it's here. Only because it's notationally nicer to do that. But I agree, usually when you have something you're penalizing, you would put the coefficient in front of the d bar. Yeah. Any other questions? Great, so this is the NPG optimization problem, right? So maximize alpha surrogate advantage minus average KL divergence. So this is very hard to maximize in any kind of analytic fashion. So what we're going to do is approximate both of these two terms. And the way that we're going to approximate these two terms is we're going to say, well, I know that I shouldn't be taking massive steps in parameter space. So I know that theta nu should be pretty close to theta old. And if theta nu is pretty close to theta old, then I should be able to Taylor expand both of these two terms, so with the surrogate advantage and the average KL divergence, I should be able to Taylor expand both of these in theta nu around theta old, because theta nu is going to be close to theta old, right? So this is how I'm going to approximate this objective to allow me to obtain an analytic solution. All right, so let's go term by term. So first of all, we need to Taylor expand the surrogate advantage. So the surrogate advantage, we can Taylor expand it, and it turns out that to leading order, the surrogate advantage Taylor expanded around theta old is just theta nu minus theta old, grad theta, the policy gradient at theta old. All right? So this is the policy gradient at the previous set of parameters. And the good news is we know how to estimate this, right? So we had an entire lecture on A2C, and that was all about how do we estimate this policy gradient. So we're going to, when we get to that stage, we will estimate this thing using the A2C method. Right? Any questions? Fantastic. Okay. Now we're going to try to Taylor expand the KL divergence to leading order. And in theta nu around theta old. And it turns out that the first order expansion, so the first order expansion actually vanishes. And so the term that we're left over with is only the second order expansion. So this looks like this. We have a quadratic with a half out front of theta nu minus theta old. And the term, the matrix in this quadratic, is called the average Fisher information matrix. So the bar again is indicating an average, and we have F bar theta old, the average Fisher information matrix. And this is what this looks like. So you are averaging across trajectories drawn according to the old policy of summing over the time steps on those trajectories, the Hessian, so this is the Hessian out here, of the log probability of each action given each state according to the old policy. Okay? So this thing is called the average Fisher information matrix, and it can be written like this. And this turns out to be the second order Taylor expansion of the average KL divergence. So this is where it comes from. All right? So we have both of our terms in the objective, the surrogate advantage and the average KL divergence, and we've Taylor expanded them both to leading order. And now we're going to substitute them in to get an objective that we can analytically maximize. So this is the natural policy gradient sort of theoretical objective, what we'd really like to do, but we can't do that. So instead, we're going to Taylor expand. The Taylor expand both terms, and that gets us this beast here, right? So the first term becomes the dot product of this distance with the policy gradient direction, and the second term becomes the inner product of these this difference with respect to the Fisher information matrix. Okay. And if you look at this, this is just now as a function of theta nu. So remember, we're maximizing this as a function of theta nu, as a function of the new policy parameters. If you look at this, this is just a quadratic expression in theta nu, right? And because it's a quadratic expression in theta nu, I can analytically write down what the maximizer is for this, right? So because it's a quadratic, I can analytically write down its maximizer, and this turns out to be theta nu is theta old plus 2 alpha average Fisher information matrix inverse policy gradient direction. All right. So we'll just go through each term and see how to interpret it. So this term, the policy gradient, means that we are moving in a direction of increasing return. So we're trying to increase the return. So this makes sense, right? We want to update our parameters, and we should be moving our parameters in a direction that increases the average return. This term here, the average Fisher information matrix inverse, is a correction that we apply to this direction to minimize the distance from the old policy. So this is a correction that keeps the two policies close, or tries to keep them as close as you can while still increasing the return. And lastly, this term out front, the 2 alpha, is a learning rate. So we see that the alpha here coefficient that I put in front of the surrogate advantage ends up translating into a learning rate. So theta nu is theta old plus something, and the coefficient that I have out front, this 2 alpha, is the learning rate with respect to which I'm applying these updates. Does anyone have any questions about this? Yeah.
Can you offer maybe more or different intuition on, say, the appearance of the Fisher information matrix? Can you interpret this in terms of, say, curvature or sharpness? Because that's the context in which I kind of...
Yes. So the question was, can we have like an alternative interpretation of the average Fisher information matrix? And you're entirely right that another way to interpret this is as a curvature term. So you're, the thing that you're really doing is that this gives you an update direction in parameter space, right? So the policy gradient, the grad theta calligraphic j theta old, this is an update direction in parameter space. But what you really want to do is compute an update direction in policy space. Because what you really care about is when I compute a update in parameter space, right? When I do this kind of update in parameter space, I'm trying to look for adjusting my parameters in a way where I'm keeping the adjustments small, right? But what I actually want is to update my parameters in a way that keeps the policy distance small, so the change in policy small. And this Fisher information matrix, the inverse of it, basically translates from an update in parameter space, which is what you get from the policy gradient, the term on the far left there. It translates from an update in parameter space to an update in policy space instead. So that's how you can interpret this, that it's translating between a parameter space update and a policy space update, so that you're performing an update in the sort of space of policies to keep the policies close to one another. Does that make sense?
Yeah.
Any other questions? Great, awesome. So we now have a expression for the natural policy gradient direction. And now the problem is, how do we compute this? How do we compute the natural policy gradient direction? So this is the update rule we're trying to apply. Let's start with the policy gradient, right? So this grad theta calligraphic j theta alt. This is just this expression here, which I'm going to call g hat, right? So all I've done here is I've taken the expectation and I've replaced it with a sample over a data set of trajectories. So we'll probably be familiar from this from previous lectures, but the way I would actually apply this is I get my current policy, so my theta old, I do a collection of rollouts in the environment, I gather a data set D of trajectories according to those rollouts, and then I'm averaging over those trajectories, summing over the time steps of those trajectories, approximating the advantage estimates, and then doing grad log pi action given state, right? So this is just the same estimator that I formed when I was doing A2C. And we're going to call this estimator g hat throughout. And I'll remind you that there's many ways of computing these advantage estimates. Typically, you would do it with a value function of some kind. There's the reinforced with baseline advantage estimate, where you take the return and then you take away the state value. And then another popular one is the TD error advantage estimate, where you do that the action value is the reward plus discount factor value of next state, and then you take away the estimated state value according to your state value function. So we saw in the A2C lecture, we discussed various ways that I can learn and form advantage estimates. So we're not going to go back through that today. If you need to refresh your memory, you can go back to that previous lecture. But the point is that I form my advantage estimates, and then I use them as weightings for this grad log probability, and then I average over a data set of rollouts, and this gets me my estimator for the policy gradient. Okay? So this is all just stuff we covered in the A2C lecture. All right, so I've got this part of it, grad theta j theta old. Now I need this part of it. So first of all, let's cover the sort of naive method of computing the natural policy gradient direction. So what I want is to compute this thing here. So f bar theta old inverse g hat. So what's sort of the most obvious way to go about doing this? Any suggestions? So probably the easiest way, or like the most straightforward way, is, well, I want to compute the inverse of a matrix times a gradient, or times a vector, g hat. So all I'm going to do is I'm going to compute this matrix, invert it, and then apply it to this vector, right?
That's symmetric, right?
It is symmetric, yes. So you can do some additional tricks to speed up the inversion process, and it's also actually positive definite, so you can apply actually more tricks to speed up inversion. But the basic premise of the naive method is I'm going to compute this matrix, and then I'm going to invert it, right? And then I'm going to apply it to this vector. So let's start with how am I going to compute f bar theta old. So there's actually an alternative expression for the Fisher information matrix that goes like this. Expectation under rollouts according to my old policy of the outer product of the gradient of the log probability of each action given each state with itself, right? So this outer product here. Why is this a helpful expression? The reason this is a helpful expression is because if I go back to my A2C estimator, I'm already computing grad theta log pi, right? So I'm already computing this grad theta log pi A given S. And so if I've already got that, all I need to do is I take those vectors, I compute the outer product of those vectors with themselves, and then I average across a data set of rollouts to form an empirical average of this expectation, and summing over the time steps. So if if I do that, if I use my empirical Monte Carlo estimator for this, I get this beast here, right? So average over a data set of trajectories, summing over the time steps, and then this outer product of the grad theta log pi a given s, right? Does this make sense? People have questions about this? Cool, great. So this is a somewhat efficient way to compute this Fisher information matrix because I'm already computing these vectors. And if I'm already computing these vectors, what I need to do is then take out a products and sum and then average, right? So I have this approximation for theta old, and the naive method just goes, well, let's take this approximation, let's invert it, and then let's apply it to this vector. So first of all, if I do this, if I form this matrix using this method, I then invert the matrix and then I apply it to the vector. What is the space complexity of this method in the number of parameters that I have? So in the number of parameters theta. Does anyone have any ideas? So space complexity. How does the amount of space or amount of memory I need to allocate change as I increase the number of parameters? So because I'm storing a matrix that is number of parameters by number of parameters, the storage requirement goes as order p squared, right? It's quadratic in the number of parameters because I have to store a matrix that is that number of parameters by that number of parameters in size, right? No, so time complexity is actually even worse. It's O p cubed because I have to do this matrix inversion here, right? So it's OP squared to form this this matrix, but then the inversion of it is OP cubed. You can actually, as I'm sure you all know, you can do better than OP cubed. So there are matrix inversion algorithms that do better than cubic in the time, but they don't do better than quadratic in the time. So at best, you're getting something that's they don't get particularly close. So it's around order p squared in the number of parameters to compute this gradient estimate. So this scales poorly when you have a large number of parameters. So remember, p is the number of parameters in my neural network, and if I have, say, if I want to make my network 10 times larger, this is going to take 100 times as long and require 100 times as much space. So this is not a very efficient way of doing this because it scales quite poorly with the number of parameters that I've got in my network. Does anyone have any questions before we move on? Great. So now let's cover another way that we can compute the natural policy gradient direction called the conjugate gradient method that actually does this much more efficiently. So there's lots of moving parts here, and we'll cover them one by one. So first, let's consider a different problem, right? So before, we were trying to compute the average Fisher information matrix inverse applied to g hat. But now let's ask, okay, how can I efficiently compute the Fisher information, the average Fisher information, not inverted, applied to an arbitrary vector v? So you give me a vector v. How can I efficiently compute this this product here, this matrix vector product here? All right. So we saw in the original definition of the average Fisher information matrix that it is the Hessian, so this grad theta transpose, of the log of this this probability here. So all I'm doing here is I'm taking my expression for the average Fisher information matrix, and I'm just expanding this out. And then I'm going to take this thing and apply it to V. All right? But now I can note that I can move this V inside and treat this grad theta transpose as acting, or once I've taken this grad theta transpose, it then acts on the V. So this expression here is mathematically equivalent to this expression here, where what I'm doing is I'm first doing V dot, so V transpose, grad theta, so getting the gradient direction, or getting the alignment of the gradient with V of my log probabilities of action given states, and then taking the gradient of that again, right? And then again, I'm going to take an empirical estimate. So I'm going to average over, I'm going to replace this expectation over trajectories drawn according to the old policy with an average over a data set of trajectories drawn according to the old policy. So this expression here is called the Hessian vector product trick, or sometimes Perlmutter's trick. And essentially what it allows us to do is to compute the Hessian, so the average Fisher information matrix at the old set of parameters, applied to a vector with order p space complexity and order p time complexity. So the space complexity for this is only order p, and so is the time complexity for this. The reason for this is that all I need to do is I take this function here, so log pi is a function of the set of parameters, and I take its gradient, right? And this gives me a vector, where if I put in a particular set of parameters, I now have a vector in parameter space. Then I'm going to align this vector, take the inner product of this vector with a particular direction v that I'm interested in. And this gives me a function that takes in a set of parameters and computes a scalar, right? So the grad theta gives me a vector in parameter space, and taking the inner product with a particular direction gives me then just a single scalar. So this is then a function of the set of parameters at a particular, a function of a set of parameters that takes in sets of parameters and spits out single values, spits out scalars. And then I'm going to take a gradient of this. And so at no point do I need to compute anything that has size or memory over p, right? So this vector and this vector both live in p-dimensional space, and then I'm taking the inner product of them to get something that lives in one-dimensional space, a scalar, and I'm taking a vector again to get me back to a p-dimensional space. So my space complexity never goes above p, and my time complexity is also only order p, because taking this gradient is order p, and taking the second gradient is also order p acting on this scalar. Does anyone have questions about this? This is perhaps like the conceptually hardest part of this lecture. So this Hessian vector product trick, or Perlmutter's trick, allows us to compute the average Fisher information matrix acting on a vector in only order p time and order p space complexity. And this scales very favorably with the number of parameters. So this method of computing this is very efficient and doesn't require that much space or that much time. So we have a method, which is the Hessian vector product trick, of computing average Fisher information matrix applied to a vector v. But this isn't actually what we want, right? What we want is the inverse matrix applied to some vector, right? So what we need to do now is solve the second layer of the problem, which is, okay, I can very efficiently compute this thing, so f bar v, and now I need a way to use my ability to compute f bar v to compute f bar inverse g hat, all right? So that's the second layer of the challenge. So how are we going to do this? So one way to do it is to consider the following quadratic, right? So this is a quadratic in x, and it's x dot f bar x minus xg. Now, if you take the, this would be a positive definite, so a convex function. And if I want to minimize it, that means I can just take the gradient and set it to 0. If I take the gradient and set it to 0 and rearrange, I'm going to see that the minimizer of this quadratic is indeed f bar inverse g hat. Right? So you can maybe do this in your head and rearrange it a little bit, and you see that the minimizer of this quadratic is f bar inverse g hat. And so if I can compute something that approximately minimizes this quadratic, I can compute something that approximates f bar inverse g hat. This makes sense? I know what the minimizer is. If I can compute an approximate minimizer, I can compute an approximation to this quantity here. All right? This is the basic logic. So if I take the gradient of L, take this gradient of L, I can see that it's equal to this. right? And if I set this to 0 and rearrange, I get that x, the minimizer should be this. But if I'm just interested in the gradient, you can see that computing the gradient only requires the ability to compute f bar v for arbitrary v's, right? Because computing the gradient only requires this f bar x, right? And so if I can very efficiently compute the f bar acting on any vector I like, acting on an arbitrary vector, it means that I can very efficiently compute gradients of this quadratic. And so the logic is that I can very efficiently compute gradients of this quadratic, and so I can do gradient descent on this quadratic to approximate f bar inverse g hat. And I can do this only using the ability to compute f bar v. So doing gradient descent on this quadratic, it's a way to translate my ability to very efficiently compute f bar v for an arbitrary vector v and translate that into an approximation for f bar inverse g hat. Does anyone have any questions about this? Cool. Okay. So it turns out that doing gradient descent is not the best thing you can do. So you could do this and it will get you an approximation, but it's not the best approximation you can use. A better way to do it is to so we're trying to minimize a positive definite quadratic function. It turns out that this is, convex optimization as a field cares a lot about this problem, and there are lots of methods within convex optimization for solving this problem. And one method that works very well is the conjugate gradient method, which is why I've called this whole section conjugate gradients. So a better method is the conjugate gradient method for minimizing a quadratic, and I'm not going to go into it because it's very complicated. If you're interested, I encourage reading up on it. But the bottom line is, the important thing is, just as with gradient descent, to use the conjugate gradient method, I only need the ability to compute f bar v for an arbitrary v. So I only need the ability to compute this matrix vector product, and I know that I can do that very efficiently, right? So in practice, what we'd actually use is the conjugate gradient method as a way to approximate the minimizer of this quadratic, which we know is the thing that we're trying to get anyway. So the conjugate gradient method, to summarize the overall approach to computing the natural policy gradient direction, we compute the Hessian vector product, so the average Fisher information matrix applied to a vector, using an empirical average over a data set of trajectories of this Hessian vector product trick, or Perlmutter's trick, where we compute the gradient direction, take an inner product, and then take a gradient of that scalar function that we obtained there. All right? And then once we've got this, or once we know how to do this, we're then going to perform a fixed number, so capital K, a fixed number of conjugate gradient update steps on this quadratic function here. And this only requires the ability to compute this f bar v for an arbitrary v. All right? So the space complexity of this, at no point do I need to store any quantity that's bigger than the number of parameters that I have, right? So this also only has order p space complexity. So it scales very favorably with the number of parameters in my model. What about the time complexity? So each computation of this Hessian vector product is order p time complexity, and I'm going to need to compute capital K Hessian vector products to use the conjugate gradient method. And so my time complexity is capital O, so big O, Kp, right? And typically, K is chosen to be much, much smaller than P. So your P would realistically be at least hundreds, maybe thousands, and K might be something like 20, right? So a very small number compared to P. So typically, K is much, much smaller than P, and this gives very favorable scaling with P. It's much nicer and much better than the scaling with P that you get when you use the naive method. I have left it out, but I will briefly mention here that often we add a small perturbation of a constant diagonal matrix, so a scalar multiple of the identity matrix, to this Fisher information matrix here. So we could alternatively do it here instead. This just helps numerical stability issues. So this is just an implementation detail, briefly mentioning it, not going to cover it in a lot of detail. Does anyone have any questions about this? Okay, great. So this is the conjugate gradient method, and it's a much more efficient way of computing the natural policy gradient direction than the naive way of compute a matrix and then invert that matrix. Okay, so we know how natural policy gradient works. Now let's cover trust region policy optimization to sort of round out and close out the lecture. So let's return to the overall optimization problem of today's lecture. What we want to do is maximize the surrogate advantage. So maximize this, which we know that when these are close, this approximates the policy improvement. So when the policies are close, this approximates policy improvement. And we want to minimize the average KL divergence. We don't want to let the new policy get too far away from the old policy. Okay? So the TRPO objective differs from the, so in the natural policy gradient objective, we are penalizing distance, right? We're taking the surrogate advantage and we're penalizing how far away we are. In trust region policy optimization, instead we constrain distance. So we're not penalizing distance anymore, we're constraining distance. This is how they differ. So I'm going to maximize the surrogate advantage over all theta nu, so maximizing theta nu, over all theta nu, such that the distance under the average KL divergence is less than or equal to delta. Right? So how do we interpret this? We're trying to maximize surrogate advantage. This is our objective we're trying to maximize, subject to the constraint that the new parameters, so theta nu, are in a trust region around the old parameters. So this is a distance metric, and this defines a sort of ball in parameter space that we want to maximize this objective within that ball. So delta here controls the width of the trust region. So it controls how far away we're willing to get in this distance metric. Okay? Does this make sense? Does anyone have any questions about this?
Is d bar here scalar?
Yeah, d bar is again the average KL divergence, and this is just a scalar. Okay, so now we're moving from penalizing to instead constraining. So this is the optimization problem, this is the TRPO optimization problem, and we're going to, once again, we're just going to Taylor expand both terms. So we'll Taylor expand the surrogate advantage, and we'll Taylor expand the average KL divergence. We've already gone through these Taylor expansions. It's exactly the same as before. So we want to maximize the difference inner producted with the policy gradient direction, subject to the constraint that theta nu minus theta old, the inner product of this difference with respect to the average Fisher information matrix is less than or equal to delta. So this is just taking these constraints, taking both the objective and the constraint, and Taylor expanding. And again, this problem, you can analytically solve it. So you can analytically solve this problem using Lagrangians. I'm not going to go into how. Hopefully you've seen this before. If you haven't, it's very easy to look up. And when I do it, I'm going to get a change in delta that looks like this. So let's unpack what's going on here. So this is just the natural policy gradient update direction. So this thing here is just a scalar, so let's ignore it for now. In terms of the direction that I'm moving my parameters, the direction itself, it's just exactly the same as the natural policy gradient update direction. There's no difference. It's the same direction. But now I have an effective learning rate that is scaled according to the inner product of the natural policy gradient direction and the regular policy gradient direction, right? So this sort of controls the learning rate to keep me within the trust region. That's the purpose of this. So this is the same direction as natural policy gradient, except now I am scaling my learning rate so that instead of penalizing distance, I'm instead constraining myself to be within the ball that I define. So within this constraint that I put on the parameters, right? Okay, there's one final trick that we have to cover, and then we're done. The last two slides. So the theta nu that we found wasn't actually the analytic maximizer of this thing here, right? We found the analytic maximizer of the problem once we perform the Taylor expansion, right? So once we perform the Taylor expansion, this is the analytic maximizer. But that doesn't mean that it's actually going to satisfy this constraint here or increase this advantage here, right? So this is just an approximation, and this means that the theta nu that we found doesn't actually necessarily increase the surrogate advantage, and it doesn't actually necessarily lie within the trust region, right? We're not actually guaranteed that either of these things are true. So what we're going to do is we're going to exponentially decrease the step size until the distance constraint, so the average Cal divergence constraint, is satisfied and the surrogate advantage is positive. Okay? So we're going to start with this update direction, and then we're going to plug it into our average Cal divergence and our surrogate advantage and ask, is the surrogate advantage positive, and is the average Cal divergence less than or equal to delta? And we'll plug it in and see if that's true. If it is true, we accept this update. If it's not true, we decrease the update step size by a factor of alpha. So we pre-multiply this delta theta by alpha, and we try this theta nu. So again, we plug it into our average Cal divergence, we plug it into our surrogate advantage, and ask, are we getting positive surrogate advantage? Are we satisfying our Cal divergence constraint? If it's true, we accept this update. If it's not, we play the same game again, right? So we pre-multiply by alpha again. So this is an exponential decay in step sizes. And we keep doing this up until a maximum number of iterations, capital J. And if we haven't found anything by that, we just reject all updates and we just perform new set of rollouts with our current set of policy. All right? So this is called a backtracking line search. The reason it's called that is I start by considering a maximum update. I see if that's acceptable. If it's not, I backtrack by a factor of alpha, and I see if that's acceptable. And I keep doing this over and over again. This is a backtracking line search. Now, we're going to perform this backtracking up until the surrogate advantage, which we approximate like this, is positive. So I have a positive surrogate advantage. And again, this is positive empirical surrogate advantage. So surrogate advantage once I've sampled over a data set of trajectories. And the empirical KL divergence constraint is less than or equal to delta. So I'm just going to keep backtracking until these two conditions are satisfied. And when they are, I accept the update. I move my parameters along, and then I go back to doing rollouts. Right? So to sort of summarize the overall approach, I'm using an algorithm very similar to A2C, except now when I perform my parameter update, I don't just use the policy gradient. Instead, I'm performing this this gradient step in the direction of sort of in this adjusted direction where I'm adjusting for the fact that I want to keep the policy close to the old policy. Great. Does anyone have any final questions? Fantastic. Thank you all very much.